Hi all, very happy to be here and have the opportunity to present some of our recent work on a decentralized breeding approach that we called 3D breeding. Before getting to the research, I just want to set the stage for this talk. Indeed, I'm going to speak about smallholder farming system, and I'm sure that you are well aware that hundreds of millions of farmers in the world are smallholder farmers, and collectively they provide the livelihoods of estimated 2 billion people. And most of these farmers are in the world south. And I think that there's a number of reasons why this kind of agriculture is very interesting. One of which is that smallholder farmers experience remarkably heterogeneous conditions, both in terms of climate, but also in terms of cultural heritage and uses that are done with the crops that are cultivated. And there's a number of reasons, including these, for which by some it's been advocated that there might be room for improvement in the way breeding addresses the needs of these specific farmers. Indeed, there's an issue with varietal uptake. It might happen that varieties that are produced by international breeding efforts, centralized breeding efforts, are not chosen by local farmers because of this mismatch in what is offered from what is needed. So in this talk, I'm going to speak about smallholder farming, asking ourselves whether this is a burden, so something that we need to leave behind as soon as possible, or might be a resource. And indeed, my point is that there might be scope for bringing these farming systems fully into a data-driven research approach to try to connect traditional knowledge with modern research and modern breeding methods, starting from genomics. So my talk today, it's centered around the comparison of two alternative, well, we will see later, we will argue, complementary possibly, breeding approaches. So the first, it's what we call the benchmark. It's something that represents what is commonly done by breeding, and it's what we call centralized breeding. So there's a certain number of experimental stations in which hundreds of genotypes are characterized for their phenotypic performance, and of course they're also characterized for their genetic diversity. And combining this information through genomic selection, we can then produce predict performance in untested environment, and therefore on the basis of this develop new materials or do varietal recommendation, which is represented by this graph here. In a certain portion of space, there are some regions for which we will recommend variety A and some regions for which we will recommend variety B. The other approach that I'm comparing to this benchmark, it's what we call decentralized, 3D breeding or data-driven decentralized breeding. And the idea here is that we forget about centralized research stations where to select materials, but rather we move the selection entirely in farmer fields themselves. So we involve hundreds of farmers, each performing a simple task, which is evaluating a very limited set of varieties. And collectively, we bulk this data together, we combine it with climate and genomics, and hopefully produce a better varietal recommendation, which has a finer spatial grain, depending on local adaptation, and higher accuracy, and by this higher genetic gain in breeding for smallholder agriculture or challenging cropping environments. So this comparison is built around case study, which focuses on durum wheat tetraploid wheat. It's traditionally cultivated in the Ethiopian highlands, and here we are dealing with Ethiopian highlands indeed. And it's traditionally cultivated there since generations. Bread wheat, so hexaploid wheat, is also cultivated in the country, but more in the central part. In the highlands, many communities, smallholder farming communities, rely on durum wheat for food security and food preparations with cultural value and so on. So in this experimental scheme, we focus on grain yield and appreciation metrics given by farmers, which we measure on an overlapping set of durum wheat genotypes, both in centralized location, so 2 years, 2 locations, representing experimental, so to say, setting, and a decentralized field, meaning farmer fields, 1,165 of those distributed across the country. And then we try to compare how good can we predict durum wheat performance in farmer fields using a centralized approach versus a decentralized approach. So the benchmark, meaning the centralized approach, is here represented by this scheme. So we have 400 durum wheat varieties that we genotype. And as I said, we measure grain yield, but we measure also farmers' appreciation, which we term overall appreciation. And this is given in a quantitative way or a semi-quantitative way. So farmers are going across the fields in front of each plot and providing a Likert scale kind of scoring from 1 to 5, 1 meaning I don't like this variety, 5 meaning I like a lot this variety. And we conduct this experiment in a fully replicated design in 2 locations, 2 years. And at the end, we collect all these measures. And of course, grain yield, overall appreciation, it's highly correlated with grain yield. So farmers prefer high yielding varieties, which is expected, even though farmers are not measuring grain yield. They are just eyeballing the field close to flowering time. And actually, overall appreciation has a remarkably high heritability that you see here in the bottom, even higher than the one we get on grain yield. And so it's a quantitative measure that we can use for breeding. And indeed, we can do genomic selection with this kind of data. So we can use data that we collect in experimental stations and then train the model there on grain yield and overall appreciation and try to predict grain yield and overall appreciation in farmer fields. And what we see, and we use seasons as blocks for validation. So we have different performance every season, but overall, what you can see is that, well, you have positive accuracy when using grain yield to predict grain yield observed in farmer fields, and an even higher prediction accuracy when you use your model trained on overall appreciation in stations to predict overall appreciation in farmer fields. And this is a fairly good job. I mean, it's something that I would say represents what breeding does, which makes a lot of sense. So, and it achieves positive results in this regard. But the other part of the story I'm here to tell you, it's this other method, right? So it's what we call data-driven decentralized breeding, or 3D breeding for short. And here we move selection entirely in farm fields. And here I have to acknowledge Cao de Souza and Jacob Van Etten, who are driving force of this approach, and the approach is on which 3D breeding is developed, which is the triad comparison of technologies. But ideally, it's a very simple scheme. So the idea is that hundreds of farmers are given a permuted set, set of 3 varieties that they blindly evaluate at the end. So they don't know which varieties are these. They grow them in their own field. At the end of the season, they tell us which they like more and which they like less. So in a ranking kind of reasoning, so that we can reconstruct the performance of each variety in each of the farmer fields. And the trick here is that, of course, this is a highly unreplicated decentralized approach, so that each farmer gets only 3 varieties, right? And a different set of varieties. So the first farmer gets variety A, C, and D. So they will tell us that variety A is the best one and D is the worst one. So we can derive that C is the middle one. The other farmer will get C, D, and G, and we'll end up with a different ranking. And so by putting together all these rankings for more than 1,100 of farmers, we can reconstruct the full picture and estimate what is called the worth of a genotype. So you can see that as a propension of outperforming other genotypes. And this is done with a Plackett-Luce model. And the model, it's built considering climate at the testing location and genetics, so genetic diversity of the varieties. And depending on these covariates, the decision tree can split and you can have different outcomes in terms of worthiness. So you can end up having very precise measures of estimated performance in local conditions. And then you can build prediction on this. And this is the key finding that I'm here to show you. What we see here, it's that if we use 3D breeding, we get basically twice the accuracy that we get to do the same task using a centralized breeding approach. And this is on the left, it's what I show you before in the plot. You see, this is the accuracy, so the correlation between the estimated value and the observed value for overall appreciation in grain yield that we get using a centralized breeding kind of mindset, so 0.14 and 0.04. And we get basically double that if we forget about centralization and we use decentralized fields to predict other decentralized fields. So why this happens, why 3D breeding methods in our hand it's working in this way. Many reasons for that. Happy to discuss them, but probably a good summary of that. It's represented by this principal component analysis here, where we show the environmental diversity at the test sites. What you see here, it's PC space, which represents variation in temperature. The gray dots are the experimental stations that we used, and the other dots are the farmer fields. And you see that, of course, the centralized station cannot cover the entire environmental diversity which is experienced by farmers. And this is not because these stations are not representative. These stations are representative, are used actually to support breeding decisions in Ethiopia. It's just that there's a trade-off here, because of course, there's only that many centralized stations that you can use to fully characterize your materials. But you will not efficiently capture the full diversity that is found in the target fields for this kind of breeding decision. And of course, the trade-off for 3D breeding is that you are using a non-replicated, not fully replicated design, partially replicated design, and that you can test less genotypes. But still, with this trade-off in hand, I showed you that in our case, 3D breeding can double the accuracy of centralized breeding for predicting overall and grainy. And this is also why the method is called 3D breeding, not only because it's an acronym, but also because it tries to capture 3 dimensions of crop performance in farmer fields. So meaning not only genotypes, environment, but also management. And if you go back to the genetics of it, you see these are PCA, this time representing the genetic diversity between varieties included in the study. You see there's a big gap in here. These are Ethiopian durum wheat land races. So these are lines produced by international breeding and currently recommended as durum wheat in the Ethiopian highlands. And you see that there is a gap in the genetics, but there's also a gap in the kind of varieties which are recommended by our methods instead of varieties which are currently recommended. So there is scope to harness more diversity, both in genetic terms, which is, diversity in land races, and in environmental terms, in terms of varieties which are, in terms of conditions, which are experienced by farmers. And actually, I don't have time now to go into this, but you're welcome to look into the paper, which was recently published on communication biology. We found that this method is consistent across simulated seasons. So we think it's a fairly solid kind of procedure. And I realize this is a lot to take. This presentation probably it's dealing with something which is not very common and might sound a bit of out of the blue, but I would say it's not. And I want to conclude with a few remarks, which I think are really important. So the first one being, I'm not here to say that conventional breeding is wrong and 3D breeding is right. What I'm saying is that 3D breeding might complement what we call conventional breeding or centralized breeding. So this kind of data-driven decentralized breeding, it's something that could enrich and better tailor the predictions and breeding decisions that are based upon these predictions, especially in challenging farming environments. So it might be used to refine the selection of pre-breeding materials or even to select parents for new breeding process. I would also say that 3D breeding can be generalized. Of course, here I'm speaking about durum wheat, I'm speaking about highlands of Ethiopia. But as I said at the beginning of the presentation, these kind of farming conditions are more widespread than one could think. So already in different crops in this kind of setting, I think this method can work. And indeed, there are currently research projects ongoing using this method in different crops. But also there is scope, I think, to apply that for a more conventional kind of agriculture, like the Western agriculture. Again, to tailor better decisions capturing to the fullest the diversity that is experienced in farming conditions. And finally, a note of caution, because this method, it's not really expensive. Actually, in our hands, it's cheaper than the benchmark that we used. It's a matter of resources. Of course, it's more expensive in terms of you need more seeds, you need to distribute these seeds, but it's much cheaper in terms of characterization of these materials. And of course, genotyping is not it's not very expensive nowadays. So I would say that these different methods can fully complement what is already available and support the tailoring of decisions to kind of off-types growing environments. And well, I have to thank many people for this work, of course. Already mentioned Cauê de Souza and Jacob Van Etten, but also the team at Scuola Superiore Sant'Anna, where I work, Cornell University, Kansas University, Alliance of Bioversity International, and CIAT, Carlo Fadda especially, and of course the citizen scientists who work with us. And I thank you for your attention.